Okay, the last presenter is Dr. Thiru Aravinthan from University of Southern Queensland. The title is Research and Development of Concrete-Infilled FRP Pultruded Tubes. The floor is yours.
Thank you. So today I'll give a highlight of some of the work that has been done on, particularly on the research and the development on concrete-infilled FRP tubes. At this stage, I would like to also thank my co-authors of this paper, Weena, Lokug, Majid and Ali Alsaddi. Two of them have been, one of them is a former PhD student and the last presenter is a current PhD student as well at USQ. So I'll give a short the overview of the presentation will be in the forming of looking at some of the background, review of some of the past research, and particularly focus on the work that has been done on FRP tubes as girders and the work that has been doing or currently being done as an axial member, particularly in the application of columns, and with some concluding remarks. Now, some of the early studies, probably you would have heard a lot about this, how as a concrete engineer we look at concrete structures and then start to look at how do we enhance its performance and how we use FRP, whether carbon, glass, in various forms, and then start looking at this has been done over the years. In the last 20 or 30 years, a lot of work has been done. So concrete structures, how do we enhance that? So then people start to look at a little bit differently. Now, can we combine this and make the FRP or fiber reinforced polymers as one of the main component and also use concrete together with that? And this has resulted in some of the configuration as you would see here, like the concrete part followed by glass fiber laminates and more carbon at the bottom fibers instead of steel reinforcement. So that has resulted in these kind of structures. And work has been done in this, particularly in the past by some of the work at our university as well as in other universities. People have done work on these areas. So particularly Amar Kenane from University of New South Wales in ADFA, and also at University of Adelaide there had been work done and well published in this. Then it went on to various other aspects of, okay, we have got these composites, how do we make use of that, and can that really be a product that can be go into mass production as well as into the general civil infrastructure. And then we currently have various producers who produce pultruded sections in various forms, various shapes, I shapes, circular, square, and so on. And depending on the type of manufacturing, you will find some interesting products coming out into the market. And currently this is being promoted by the people who are producing this, the manufacturers. They are quite keen to get this into the market, and then as researchers we start to question how much it could be used and how it could be used, what are the issues and what challenges we have. So these are some of the things we look at as researchers and in the academia or in the R&D organizations. Now, pultrusions is commonly used in using FRP composites. Carbon fibers, glass fibers has been heavily used in pultruded sections. But in addition to the normal pultrusions, which is mainly you get the fibers in the main direction, in the zero direction, in the axial where it is being pulled. Then you have got the pull winding technology where you can pull the fibers as well as wind some of the fibers around that, and that can form the fibers in major direction, in the zero direction, and then you can also have plus minus like a confinement fibers forming around that. So those are manufactured by pull winding technology where you will get fibers in this direction and also in plus minus 45 in this direction where it's a continuous fiber that is manufactured and woven through that one. So only a few manufacturers in the world who have got this technology developed. And so what we have looked at is, okay, how do these pultruded products? So we have got one particular manufacturer in Australia who has developed some products, particularly using 100 millimeters, so this is in millimeters, 4 inch or 5 inch, and flats and other things. So basically 5 millimeter or 6.5 millimeters, it is little bit about quarter inch thickness, and it is 5 inch square or 4 inch square in the US, where we use the SI units 100 millimeters or 125 millimeters in Australia and other places. So how are these products being used? The things we look at beam application, girders in the form of bridges and so on. And if we look at some of those applications, you will find these are these pultruded sections that are being used as main girders, cross girders, and in some cases even as columns. And then that can lead into pedestrian walkways and other bridge structures and so on. And these have gone into some applications. These are using pultruded sections. And some other modularized of those pultruded sections with top and bottom flanges. So here you can see 3 of those pultruded sections has been put into a combined with top and bottom flanges, typically replacing an eye girder. And then, of course, to make it to the market, you have to produce mass manufacturing. And obviously, before it goes into anything in the field, there has to be considerable testing has to be done in proof loading and also ultimate testing and fatigue testing and so on. So this has been trialed and things seems to be working. But these are some other, again, various forms of pultrusions put in cell forms, in multiple cells has been put together, and that is being used in forms. So the advantage of that is anyone who want to invest in such products, they want to make sure that product they could manufacture in mass scale, and that way they have a return in their investment rather than going by each bridge where they had to produce a different product. That can be a very costly exercise. So this is one of the bridge completed through that. Now, when we look at these FRP sections, what is our challenge? If you look at an all FRP structure, which is a linear behavior, linear material showing a linear, almost a linear characteristics, and at the end it fails without any warning, and a lot of the civil and structural engineers don't want to even touch that, because people will ask what's a ductile behavior, how much it will extend after the post-peak behavior and so on, and that becomes a challenging question. And particularly those who are familiar with timber structures, timber is the most common or most closest structure or material close to FRP, because we have got the resins and the fibers in timber structures, and similar forms is formed in these artificially manufactured products. In most of the timber design, the characteristics of these are governed by meeting deflection limits, and serviceability limit states becomes the governing criteria. Then when we use these as bridge beams, the main issue we have is how do we improve the stiffness of this, and because the flexural members, the stiffness criteria for deflection can be governing, and how do we improve that? Because when we use all FRP or hybrid FRP structures, that's what the main governing design is. So at USQ, what we have done is we have done various testings, as taken these pultruded sections as the hollow sections, and then with filled section, some parts filled, some being hollow. So here you can see, and we have tested various forms as a flexure, like a beam. How do we can we make use of this? This is a single pultruded section, hollow section being tested like a 3-point bending test. So here we have 3 cells put together, and that has been tested with hollow, and then the top one has been filled, like as you show in these figures in 3-point bending, and we got single cells and multi cells process in this, and got results that has been showing how the concrete infill can be enhancing the flexural performance of these structures. So that's what we see here when we have different concrete filled with flexural behaviors on these particular FRP tubes. By the way, are manufactured with glass fibers, so it is glass fibers and vinyl ester resin has been the main properties that is being used to get the FRP tube. So here I will show in the next slide some of the failure modes you can see when it is in flexure. So generally tension, and the top you will get compression, and depending whether you get filled or not, you might not get the tension this one, but this is some of the compression failures that is happening, and these are some typical characteristic failure modes you will observe when we get beams failing under this. So going through these results, what we find is when we go through the number of cells being increased with the strength characteristics with hollow and compared to a filled concrete, and here as we get the number of bonded cells, we find the stiffness can be enhanced, and also by producing this we can improve the flexural performance. So this is as a beam we could use or a flexural member, and then we can see there are some key results. What we have got is concrete infill can prevent local buckling, and the failure load can be increased by about 1.4 times, 40% extra, so 1.4 times extra. Then multi-cell beams show much better flexural performance, as well as by only filling the top cell rather than filling the whole multiple cells, we can improve the characteristics in a much better way, because we are giving the compressive side of being filled, and then of course the concrete infilled tubes that increases the apparent modulus as well, basically increasing the stiffness of the product. So these are some of the work what we have done. Then we look at how these FRP tubes are used in different forms. As an axial member, what are the applications? Yes, you can basically drive this one into ground, particularly in salt water or environmentally challenging in hazardous in certain areas where concrete or steel piles are not used. So these are being actually used in reality in actual sites, and this is some of the driving process. And here you can see these are basically the pultruded tubes that are being used as the column or the strut for that walkway. Again, it's a combination of pultruded tubes in axial and flexural members being used. Now when we go into research into axial members, there are questions on slenderness ratios, stiffness, and what are the instability condition, global buckling, local buckling, and how of this interaction between global and local buckling. So these are some of the issues we face. And people have done some research, particularly, this is about 15 years ago, people have done research on the form of, on the slenderness ratio and some of the behavior of such columns. And obviously, typically in an I section, they have used other forms. This has been done in recent years, and I sections has been quite common, where carbon fibers have been used and glass fibers have been used, or hybrid sections have been used. And some of the results does show, yes, how the short columns to intermediate columns and other columns can have impact with the loads and the ratios of these, how these are impacting. So based on this, we have done some preliminary studies. So what we looked at is, we get various products these days. So can we look at some variables and see how these variables are affecting? For example, we do get square sections, then you can get circular sections, And some of these square sections, while it looks very similar, coming from different manufacturers, one has got almost mainly fibers in the main direction, the other one has got fibers in the main as well as using pull winding technology. Similarly, the circular sections also has got part of the confined fibers wrapped around on the sides, while some others are not. So what we have done is, as a preliminary work, I'll just show some of the tests we have done and some results, and then we have filled part of it with concrete, different strengths of concrete, basically to vary the stiffness, and also different materials, so where we could enhance the stiffness or concrete based, perlite based products and so on. So here, these are some of the interesting results what you will get. Yes, you can. This is about I think the 100 millimeter 4 inch, so that 5 times of that height approximately. Yes, the failure is, it is all, you start to cracks on the sides, and when there are no pull winding or additional confining fibers, that's the type of failure we get, and inside almost the concrete part is fully intact. And these are some of the things. And when you have the fibers, you get a different failure mode where this part is still intact, but you start to get a failure at the top. So these are some of the behaviors we are observing on the failures. And similarly, I'll show some figures here in the circular sections. These, you can see those fibers in plus minus roughly around 56 degrees, and there are some more tightly wound one around 70 degrees, so on. So there is no failure happening in this around in the midsection, but it starts to load, and only at the very end you get failures at the top, and then that's the ultimate failure we observe. And obviously in some cases, yes, it has gone, and then you get a little bit of crushing pure compression type of failure as well. So these are some of the interesting results. These are very early stages of testing. This has been done just a couple of months ago. The test has been done, and the initial result shows, yes, when you have certain filled concrete, we get a much better behavior. And in some of these cases, depending on the type of cementitious material we are using and the post peak behavior, it also is interesting to note where this is the hollow core one, and this is with filled, and this is with further filled, and different stiffness and different strength, where you can sustain certain load, and around 20 to 30% in some cases, sometimes at around 50% of the ultimate peak load has been sustained and continuous, and basically we can't fail it. It fails at much larger deflections or axial deformations. So similar failures we have observed in square sections and also in circular tubes. So these are some of the preliminary work what we have done, and this we'll be publishing further once we have summarized all of this. So I thought it will be good to share here. And in conclusions, what are we seeing? We have reviewed some of the work on FRP pultruded sections as a concrete infilled section has been conducted, and what we find is it is important to understand the properties of the FRP tubes and how we can enhance it by having appropriately infilled concrete materials, concrete infills. But in the case of pultruded beams, we do get indications there are reasonable increase in stiffness due to concrete infills, and there has been work has been done and published. But when it comes to columns, we need to understand, and also in the form of beams, multi-cell beams shows better performance, and particularly optimally filling certain parts of the cells. And when it comes to columns, we had to really look at how these has to be axial members. While some of the results are promising, we need to do further work, and that work is currently in progress. I think with that I would like to conclude my presentation here, and if you have any questions, I'm happy to answer. Thank you very much.
said, floor is open for questions. Yeah.
Mutsuyoshi from Saito University, Japan. Well, I understand, so you are using a lot of the FRP to the actual structure in Australia. So may I ask you about the initial cost and comparing to the ordinary materials such as concrete and timber? And so how much % of the increase of the initial cost do you allow when you use FRP?
I think that's an important and interesting question. When it comes to initial material cost, I would say FRP structures are costing higher. And depending on the manufacturing products and the manufacturing process, it can vary from in the form of around 20% to as high as 100% in the form of materials only. But I think when it comes to product or the project, this is where some of the asset owners, they start to, particularly the manufacturers and the contractors, what they basically claim is the easy installation and the quick installation, lightweight, all of that substantially reduces the other cost involved in the project itself. And sometimes that way it becomes only marginally increased by about 15 to 20% or so. And in some cases, it is also almost cost comparable with other products. So those are some of the aspects when it comes to overall project cost of it. But material cost wise, yes, definitely currently FRP is still material wise it is higher. And then there are probably claims, but this is still need to be substantiated about durability of that. But there are a lot of research, particularly I know it is done in Sherbrooke and other places on durability of FRP structures. While corrosion prevention is one aspect, which is good thing compared to steel, but other aspects of how the resin and the matrix will go on. So that is something still need to be done, particularly in the civil infrastructure. Other areas in automobile and aerospace, people have done that. But if we talk about the whole life cycle or the life term, it's probably much shorter compared to 50 to 100 years in a civil infrastructure. That is all. Thanks.
Hi, Thiru. Rudy Saraceno, NC State. Kind of related to Leslie's first question and the test you showed for concentric axial compression of the concrete-filled tube. I think it in part depends on how that element integrates with the rest of the structure. So, for example, what is the connection? Is the connection being made to the FRP tube? Where or are the loads being applied to that column through the concrete? And so then the expectations are different for the different components, and the behavior will be different. Because it looked like, I think you were loading those both at the interface, including both the concrete and the tube section. And so there were in some cases like a local failure of the tube just at the loading point.
Yeah, I think that's a good point. I mean, particularly, so in this case, that's where we have made sure it is concentrically loaded, both the material, I mean, the concrete and the FRP tubes. Because one of the issue we will probably, we are likely to face is once you get the settlement and the hardening of concrete, if there is a gap between that, that will create, and whether there is, in this particular case, there was no internal additional stiffness or any what I would call as like shear stiffening provided. So it was just basically the simple product as it was, and it was filled. But that will be an issue between bonding between that and how those can be overcome. But as an axial member at this stage, it has been, the concrete has been basically using like trying to push out, and then the protrusions working in like a confined product. And these are some of the things, I mean, based on preliminary testing, we see that it is promising, but there are other matters that need to be looked into in the production and I mean, how we prepare the test specimens and how much deformation we might have and how much, because this does happen not only in concrete with FRP, but also using different types of resins, because there are certain resins will have very quick, I mean, the shrinkage wise, it's much larger compared to some other resins that is being used. So these are matters when we have to look at as infills. So we'll take that into consideration. Thanks.
The question I have is service life of these products. Has any work been done on how long these resins will last when you put them out in the sun and in the environment?
Okay, I think I'm going to only answer what I know about these ones. The service life of the product, there are claims. I believe the people in the chemical, on the chemistry side of it, those who work on, say, okay, these kind of resins, this kind of matrix can perform up to a certain stage. And I'm aware there are work that has been done, particularly, I believe, Alan, you might wanted to say, at Sherbrooke, there are a lot of work has been done on the durability aspect of certain products, particularly on the matrix aspect as well. But some of the work, what has been really done is, a lot of people have done fatigue tests. So we have, at our university, we had done up to 2 million fatigue tests before one of these structure went into an actual road bridge. So that gives an indication about after so many fatigue, this one, the estimated service life would be like 60 years or 100 years, and how much how much of reduction in the ultimate, in the strength aspects of it. We have not seen much of a difference from the initial at the first loading to after cyclic loading, and having peak loads at every 200,000 testing. So we have tested like that, and we have found it is, the reduction has been overall has been around 5% or less than that. But fatigue testing is only an indication on the load carrying capacity, on the loading cycles. It does not really, this is where I would like to clarify, it does not talk about durability of the structure. And that aspect, coming to civil infrastructure, this material has been probably used about last 30 years or so, and probably in the last 10-20 years it is more than how it was at the very early stages. The durability aspect of it is still being a major question, and I believe there is a lot of work, particularly research, has to go into the durability aspect of pultruded and FRP components that goes into civil infrastructure, because we are talking about 50 to 100 years or even more lifetime. Thanks.
Okay, I think let's join Dr. Aravinthan for the great presentation. Thank you a lot.
Thank you.